Well, good afternoon, everyone. I've been asked to talk about on-farm robotics and the work that we've been doing in on-farm robotics. So to get straight into it, because we've got 10 minutes, I'll start talking about three applications. One's in tree crops, the other one's in vegetables, and the third one being in grazing livestock. So with tree crop intelligence, if we start with this because it kind of gives you a picture of how we approach the problem, and then it applies to all the other techniques that we've got as well. At the top left hand it says mobile on-farm robotics. I'll look on your left here. So mobile on-farm robotics and some intelligent sensors. And really what it comes down to is being able to place sensors of different modalities, whether it's laser, vision, thermal, infrared, radar, etc., on a mobile platform that a farmer can come along and just click on the button and it will go up and down the rows and collect large amounts of information, and from that information you start doing some interesting things. So if you can do that, then you start to write some algorithms. And the key difference between robotics, I guess, and data analytics that you see within sensor networks is that we're trying to do things in real time. We're trying to read a whole bunch of data, large amount of data, and try and process that data in real time. And the reason why we want to process that data is because we then want the robot to be able to do something at the end of the day. So once you start getting these individual features of interest, fruit, plants, leaves, twigs, whatever it might be, you can write some high-level algorithms, and those high-level algorithms could be anything that the farmer's really interested in. It's usually around the bottom part that the farmers were most interested at the beginning, so doing manual tasks like pruning or thinning or eventually harvesting as an example. But to get to that point, we've got to give the robot the capability of understanding its environment and being able to perceive its environment. And that's where the sensors kick in, the algorithms kick in, but also what that offers for the farmer is the ability to be able to do things such as crop yield estimation or crop forecasting. So this is the robot. It's a electric powered bot. It runs for about 4 or 5 hours. We put a sensor tree on it. It's got a large collection of sensors on there. You wouldn't have all these sensors on a farm, for example, but what it gives us is the capability of understanding for which tree crop, which environment is the right sensor in order to be able to capture and use that information. And the robot will go up and down the tree rows and it's collecting all this information, and then we're trying to process this data in real time as we go down. So this is just showing you on the left the vision data, and on the right is the robot detecting each individual flower. The robot can actually identify each individual tree and count how many flowers there are per tree, as well as what the density profile of those flowers are on the tree by the time it gets to the end of the row. And that information then can go back to the grower. Just before harvesting, we've done the same thing. You can go down the row and there's apples there, and on the right there you'll see the robot detecting each individual apple. And we're getting better with the sensor technology. We can start to determine size, we can start to determine different shades of colour as well as we're going through. So the difference, say now, so we went to a farmer who was a really good grower, one of Australia's best growers, and we're operating the robot on here, and they're running everything on a paddock size, or they're managing everything on a paddock size. And what this robot's doing is now giving them an individual tree, a piece of information for each individual tree, and that gives them another level of resolution with which they can work with. As an example, in one of the paddocks that we had, the farmer thought that they were going to get about so many tonnes of apples, and the way we calculated was roughly around the same amount. But what we also showed was there was a density drop in the number of apples across the paddock as you went through. And the farmer, as soon as he saw that, knew straight away what was going on, and there wasn't enough pollination trees on the other side of that farm. And there's a drop in 30% yield in that particular location. So it's information like that the farmer gets by using this type of technology. This is another example using, this is the almond farm, just going in a bit more detail about what's going on there. The robot's using the laser unit, being able to detect individual trees as it's going through. This is quite a hard problem from a robotics perspective. We've spent many years learning about models of what trees look like. To try and code that and make a robot understand is quite difficult. Once a robot can identify each individual tree, it can extract the visual data from its database as it's going through. Again, it then goes through a series of algorithms in real time, and it's able to detect individual features, such as here being able to detect individual flowers, and over here individual almonds as it's going through. And we can then map that onto something like Google Earth, and you get like a crop yield or a flower yield estimation process for the farmer, and the farmer can click on any one of those trees and then get the latest visual data that they want. So it's almost like a Google Street View of the farm for the farmer. What's of interest, I think, before I move on to the next part, was the difference between the tree crops and the almond crops is the different tree architectures. And that's going to be an important aspect as we look into the future about what future tree crop farms will look like. With the apples, they're being on trellis, so it makes it a lot easier for us to detect flowers and apples, for example. While with the almonds, because it's in a 3D kind of structure, all you can do is estimate what you see on the outside and count what you see on the outside, and based on volume, try and estimate what's on the inside. And that's going to be an important element as we start to think about business models and how automation kicks in and changing tree architectures along the way. The next one's the row crops. We've been working on solar electric vehicles now for about 4 years. The first one was Ladybird, which was more of a phenotyping robot. It had a large collection of sensors that could go up and down the vegetable rows and detect individual crops. And then subsequently got some funding to build Ripper, which is this particular robot that you see here. Early last month, we don't need the sound on this, if that's okay, thank you. Early last month we did a trial. The robot ran for 22 hours, so we started at 5:30 in the morning and it went through the day all the way till 3 o'clock the following morning. At 3 o'clock in the following morning, just stopped in the middle of the paddock because it had no more charge. And then the following day by 10 o'clock it had recharged and it went off again and started moving on from there. And it's doing the same thing. It's got a collection of sensors looking down at the vegetables, and it's just identifying each individual vegetable as it's going through. It's got a little shooting mechanism there, so as it's going through, it can actually just shoot on each individual crop as it's going through, and it does this in real time as it's going through. And this could be, I'm either trying to detect weeds and spray a bit of herbicide on a weed, or I could be looking at a crop and determining that it needs a bit of fertiliser, for example. And that's where the future of this particular project's going, and I'll look at this in a bit more detail so you can understand where the next 3 years is heading. Just an axis of yield against time, but that yield estimate could be anything. It could be crop health, for example. And what the robot's doing is it's collecting large amounts of information, and based on that, it's getting observations of what it thinks the change in yield might be as it's going through. And remember, this is for each individual crop. Okay, it's not across a paddock. It's building up an estimate for each individual plant. Then what we're also looking at is how we take in models of how plants grow and feed that into the process as well, and couple that with undercurrent conditions, whether they're weather conditions, soil conditions, business conditions, etc. How does all that information come together? The model is an interesting one because what we're finding already is that with the amount of data that we're collecting, we're starting to see potentially that the models might not be as accurate as what they are. We're collecting data 24/7 now under all weather conditions, and that could be breaking our ideas and understanding of what these models are. But what you can do now is you come along and with all that information, you can start to predict what you think the forecast will look like. But before you do that, all of this is uncertain. There's uncertainty in all these little elements. And so we're going through a process of now developing theory and algorithms and whatever it might be to project potential futures of what the crop yield looks like. And that gives the grower a little bit more of a better understanding of what the potential future might look like, and from that make a decision. There are a series of decisions that the grower can make about what to do at that particular row, or down to those particular types or classes of plants that might be in that field at that particular point in time. And what's of interest is how this grower and robot relationship will take on as we go on through the years, because that's going to become an important element. As we start to digitise a lot of this information, we're digitising a lot of agronomy, and it's going onto the robot's making a lot of these decisions. That relationship about how they learn and relearn from each other is going to be quite interesting. The final area I want to talk about is on grazing, or in the industry, is on grazing livestock. Our initial work focused a lot on how do you improve land productivity, so looking at drones over large areas, combining satellite data and UAV data to be able to detect individual weeds, as well as now starting to look at biomass. This is just an example of how we've been able to just fly over a large area. This is a 3 by 3 kilometre area, and from that pass the data into a collection of algorithms. After about an hour we can actually georeference all the weeds. This is to tell you how bad this property is, university property, and this is all serrated tussock, and so it's got a big infestation that we need to deal with. Later this month we're actually trialling a new ground robot for the cattle industry, and that's looking at, one of the things it's looking at is how do we go out there and once we've detected the weeds, being able to do something with the weeds. But while you're out there, you might as well be looking at the animals themselves, and this is an example of one of the bots that we just had a bit of fun with herding, but really what's of interest is the data that you get back when you're looking at these animals. So as the robot's going around, it's detecting each individual animal. It can detect the motion of the animal and how the animal's walking, so there's any health issues. But also more importantly, it's measuring the ground or the pasture, and so from that it's being able to determine the pasture quality and hence where the animal's spending most of its time feeding. And that becomes an important element in the dairy industry. For example, later on we're looking at milk quality as well. The last example I want to give is outside the industry, but it's really looking at how we're dealing with the educational element of it all. Underlying philosophy is that the digitization of all this shouldn't remain in the city, and how do we actually project that more out into the rural areas. So we built a bot. It's meant to be cute. The kids find it cute. You might not find it, but the kids find it cute. It's called Walla bot. It's just a die-wheel robot that can move around on a farm in different forms. But the idea is to teach kids a lot about mechatronics, about solar energy in this particular case, and about how robots work and act. But what's of interest also is the ability to be able to code up, and that's really where we're pushing this for the kids. And so what you see here is an interface where on the left, on the top left, being able to use a graphical interface to just be able to move the robot around. But there's also functional coding. So this is using Scratch, which is a type of code that allows you to do high-level coding. So all those blocks that you see on the right is the ability for a student to be able to sit down and say, go forward 400 metres, turn right 90 degrees, go, etc. So it's much higher level code, but what it teaches the students is how to code, right, in terms of a structural format. But just as importantly, as you'll see over here, as you start to play with the functional code on the right now, you'll start to see the code being generated. So as the kids get better and better at coding, they actually get to see the low-level code. So we've already got a number of schools lined up at towards the end of this year, or from now towards the end of the year, taking the robot around and just helping kids and understanding. A lot of these rural schools, as you know, have their own little plots that they work with, and being able to use the robot on those plots. Okay, so just some final thoughts on where it's all going, where I think it's all going in this space, and just being able to talk to the growers and understanding it all. The technology itself is I don't think is an issue. If you tell us now you want a certain type of bot for a certain type of farm, 3, 4, 5 months, there's a bot out there and it's being tested and it's working. Really what the issue is around business models and how we incorporate robots onto the farm, and how we have to change aspects around the farm to make robots work. So that's the first thing, I think, because when you think about putting a robot on there, there's got to be maintenance aspects to it, and there's got to be software development, there's got to be a place to store it, etc. The next thing is about how operations will change. The ability now to be able to put a robot on board, have it mobile, work 24/7, will change the way farmers will want to operate their farms, and that becomes an important element. How we understand that is going to be important. And I'm linking that also, more importantly, with plant architecture. And I think the two need to kind of work side by side as we start. If I said to you, what does the farm look like in 10 years' time? I don't want to be in a situation where I'm building a robot for farmer A that's different to farmer B, different to farmer C. What I'd like is some standards that are out there so that I can build a robot that works commonly across it. And that's the only way we're going to be able to get automation. Otherwise, the automation cost increases dramatically. A lot of work is going on now. We're seeing a lot more of this happening open source and standards, and that's going to be very important, being able to plug and play sensors onto bots and have them work properly. And we're also, as you know, as you heard very early on in this talks earlier today, there's this rapid development of hardware and software, and to maintain that, to keep that going, you've got to be able to open up the interfaces a lot more and allow that plug and play activity to happen. And finally, the technology is getting lower, cheaper and cheaper, and we're seeing that. There's going to be lots of startups. I'm still unsure whether or not they're going to have a significant impact, but I'm still unsure whether they're going to have a significant monetary impact. That's still something I don't know yet. When I look at it, I don't think there's a big space there, but to be proven. I think the education and also the knowledge transfer to digitalisation is going to be important. And really what I'm referring to there is, over the last year, the amount of people that we've had come through the lab from China, from India, from the Philippines, from Brazil, from Russia, who want to also do the same thing, automation on their farms in their own countries. And if I look at previous examples of what's happened in the past, automation is just going to bring the cost of production of crops down to its bare minimum, and that's going to be all across around the world. It doesn't matter where you're going to go, the cost of growing an apple is going to be the same. And so that's going to change the way we do business models as well, and that's something to be thinking about. So that's my attempt at looking at the business side of agribusiness. Thank you.